Okay, so good afternoon to one and all. In the previous lecture of electrical machine first, we have discussed regarding transformer or load condition. So in case of transformer on load condition, we have discussed what is the performance or what is the behavior of that transformer when it is put on somewhat load. So I think you people will understand regarding that. That is, at a no load condition, there is a current flowing from only primary winding because there is a no current flowing from secondary winding. That means secondary current it will be zero at a no load condition. So transformer it will take a current I0 from the supply to overcome the no load losses. After that, when the transformer it can be put on load condition, that means the secondary side it is closed. If the secondary side it will be closed, that means there is somewhat current it will be flowing from secondary side. Due to that current, it will produce some flux in the secondary winding. This flux it will be in the opposite direction to that of main flux. Main flux opposite direction asti. So at that situation, the resultant value of flux it will be decreases. Due to the decreased value of resultant value of flux, the EMF induced at the primary it will also decreased, and it will take a lower hand to that of supply voltage. So to meet this value, V1 is equals to E1, it will take an additional amount of current from the supply. That is I2 dash current, it will be taken from the supply. When it will take an additional amount of current from the supply, this current having a magnitude, it is nearly equal to that of secondary current, but it is the flux produced by that current, it is in same direction as that of main flux. When it will be produced as the same direction as that of main flux, the flux produced due to current I2 and flux produced due to the current I2 dash, it will get neutralized or it will cancel out. So the current or the flux it will be present in that primary and secondary winding, only main flux. At that situation, the input current taken from the supply, that is I1, it is equals to sum of vector sum of two current or vector sum of two component, that is no load current I0 and the additional amount of current taken from the supply, that is I2 dash. So it is nothing but supply current I1. So conclusion from that, it is nothing but the behavior of the transformer, either it may be on no load or it may be on full load, or on a load condition it will be a same. So this part we have already covered in the previous lecture. I have just overlooked on that part. See, today we will discuss about the losses and efficiency of the transformer. Losses and efficiency of the transformer. In an electrical machine, in an electrical machine, do you know that the loss it can be defined as the difference between, or the variation, or we can call it as a difference between input power and output power. It is nothing but loss. Suppose input we have given somewhat quantity and we got obtain or we obtain a output somewhat quantity. If there is a difference between input power and output power, so this difference we can call it as a loss. So काय तो difference असेल, suppose primary or supply voltage, it can be supply power, it can be given to that of transformer, it is nothing but support, it is 100 watt. Okay, suppose it is nothing but 100 watt, that is supply power it can be given, and at the output side we got suppose near about 80 watt. So difference between these two, that is 100 minus 80, it is nothing but 20 watt. It is the loss of that transformer. So all of you understood the definition of loss is that, or it can be defined as, it is the difference between input power and output power, it is called as loss. Okay, now do you know that a transformer it is a static device? So electrical transformer it is a static device. That means it will not contain any one of the rotating part, so that the rotating losses like a mechanical losses it will be absent in case of transformer as compared to that of other electrical machine like a DC generator or it may be motor or generator she compare karta. Transformer it is an static device, so that there is no losses there is a no friction, or we can call it as a windage losses, like a mechanical losses or stray load losses, it should be present in case of transformer. So transformer, it will be consist of only two types of losses. Again, one called as a constant loss, one it is called as a variable loss. So under the constant losses, the losses it will becomes like iron loss and eddy current loss. Only these two types of losses it will become in the transformer constant losses. And variable losses, it is nothing but it is similar to that of DC machine or DC generator or motor. It is depends upon current, or we can call it as a copper loss, because it should be depends upon current. Okay, so see, all of you understood. There are main two types of losses in case of transformer. First one constant, second one is that variable losses. So constant losses, in that constant losses, the iron loss and the electrical losses, it should be present. That is iron loss, or we can call it as a core losses. In that iron and core losses, again there is a hysteresis loss and eddy current loss. Okay, and the copper losses, it is nothing but it should be depends upon the value of current flowing from that circuit. So these are the copper losses, it should be present in case of transformer. Okay, so see, we will see and mechanical losses, it should not be present because there is a no any rotating part. So the mechanical losses, it should be 0. Okay, so this is related to losses in case of transformer. Now we will discuss one by one losses, that is constant loss, or we can call it as a core loss and iron loss. How it can be formed, that means why it is called as constant losses, and these losses, how much quantity it will be occur, or it is depends upon which parameter. See, in the core losses, there are again two types of losses. Core losses मध्ये दोन टाइपचे losses येतात. In that first one, in the core losses, again there are two types of losses, in the eddy current loss and hysteresis loss. Okay, so see, these constant losses, or we can call it as a eddy current and hysteresis loss, it should be depends upon the magnetic property of material used for the construction of core. Okay, you people know that the transformer, it will consist of one core, main part of the transformer, that is core, one of the winding and one of the insulating material. So we are manufacturing the core, and we are manufacturing the core having a low reluctance material, or having a low reluctance, that means its magnetic property, it should be good. So depends upon the magnetic property of that core material, the two types of losses are there, that is eddy current loss and the hysteresis loss. That means these losses, it should be depends upon the magnetic property of the material used for the construction of core. Okay, hence these losses are known as core loss, or we can call it as iron loss. And see, once we have manufactured the transformer by taking one magnetic material, whether there is a change in that magnetic property while it is working, while the transformer it is working, whether there is any change in the magnetic property, चेंज होईल का काय मॅग्नेटिक प्रॉपर्टी मध्ये? गिव्ह मी रिप्लाय. Once we have selected one material, suppose having some magnetic property, we have selected a material, if and it will produce somewhat loss at this condition, whether there is any change in that magnetic property once we have constructed. एकदा कंस्ट्रक्ट केल्यानंतर त्याच्या प्रॉपर्टी मध्ये काही चेंज होईल का?
No, sir.
No change in that property, so that we can call it as a this loss, it will be occur, that is constant loss, it will be occur, and it should not be depends upon the value of load, or it may be any other things. Like, see, this eddy current and hysteresis loss, it should be depends upon the magnetic property of material used for the construction of core. Hence these types of losses, we can call it as a core loss or iron loss, or we can call it as a constant loss. Okay, now see, we will see one by one how the hysteresis losses it will be occur. and how the ED current loss will be occur, and then what is meant by ED current. We will discuss that. See, hysteresis loss in the transformer. So see, do you know that the BH curve? I think you people know the BH curve. Have you know BH curve? You have already studied for DSY student. You have already studied in the diploma. First year student, that means from first year you have already discussed regarding BH curve. That is magnetic density and magnetic strength of the material. So this is a plotted curve. It is nothing but BH curve. See, the hysteresis loss, it is due to the reversal of magnetization in the transformer core. How the hysteresis loss it will be occur? So in case of BH curve, there is a reversal of magnetization. I think if you people saw the curve, otherwise I will draw here the BH curve. See, here it is B, it can be plotted. Here it is EH. So this curve, it will be like this. It will be start from here. Again, it will be like as a reversal of magnetization. Okay. So this is nothing but suppose it is started from here and this will be reverses back or reversal of magnetization. This magnetization, it will be get reversed. Okay. So this hysteresis loss, it will be occur due to the reversal of magnetization in the transformer core. Transformer core made, there is a reversal of magnetization, it will be occur, and due to that reversal of magnetization, curve, there is a hysteresis loss, it will be occur. So this hysteresis loss, it should be depends upon the volume and grade of the iron used. Which types of grade, that means which grade iron it can be used for manufacturing of the core, and what is the volume of that core. Also it is depends upon frequency of magnetization, magnetic reversal. So it is also depends upon frequency of magnetic reversal, and it is depends upon value of flux density. So it can be represented by using a Steinmetz formula, or Steinmetz, it is represented the equation of hysteresis loss, that is WH, it is equals to hysteresis loss equation represent केलं आहे बघा, that is WH, it is equals to WH, it is equals to, so here WH is nothing but hysteresis loss, it is equals to eta P max raised to power 1.6 into F into V. See, this WH is nothing but hysteresis loss. It should be depends upon volume and grade of the iron. It should be depends upon frequency of magnetic reversal, and it should be depends upon value of flux density. So that according to the Steinmetz formula, or it may be according to the Steinmetz formula, it can be represented by WH or loss, that is hysteresis loss. It is equals to eta into B max raised to power 1.6 F into V, it is in the watt. Okay, F into V, it is in the watt. All of you note down this equation, because this equation it is useful while calculating problem. So if in case of, if you are preparing for GATE examination, some problem, it should be depends upon this formula. Okay, so WH, it is nothing but hysteresis loss, it is equals to eta, where eta is nothing but Steinmetz hysteresis constant. Eta is nothing but Steinmetz hysteresis constant, and V is nothing but volume of the core in meter cube. Volume of the core in meter cube. Okay. And F is nothing but the frequency of magnetic reversal. And do you know that the B max is nothing but magnetic flux density. Okay, magnetic flux density. So all of you keep in mind the hysteresis loss of the transformer. Hysteresis loss of the transformer. It is depends upon hysteresis loss of the transformer. It is depends upon the volume and the grade of the iron core used, again it is depends upon the frequency of magnetic reversal, and it is depends upon a flux density. So the equation becomes WH, it is equals to eta, according to Steinmetz's formula, it is equals to eta Bmax raised to power 1.6 into F into V, it is in watt. Okay, so this is related to ED current hysteresis loss. Now see ED current loss. What is meant by ED current? First of all, we will discuss regarding that, and then how this loss it will be occur. Okay. Now see, uh, in case of transformer, when the AC current it can be supplied to the top primary winding, which sets a magnetic flux. See, I will draw for diagram for this. Suppose this is one of the transformer, and here it is an primary winding of the transformer. This one is the secondary winding of the transformer. Suppose supply it can be given to that of primary winding. Primary winding la kai kela apan supply voltage it can be provided. On the secondary winding, one of the voltmeter it can be connected to measure the voltage. See, when the supply it can be given to that of primary winding, when the current start flowing from this primary winding, it will set up some flux. Okay, so it will set up some flux. That means there is a magnetic field it will be created, right? Hello.
Yes, sir.
Okay, now when this flux created by the primary winding, it will travel to the secondary winding, or when it links with that of secondary winding. आता हे create झालेले flux काय होणार? It will be traveling in the core, that is path between the core, and it will links to that of secondary, right? When it will be links to that of secondary, it will produces some EMF in the secondary side. It is it is according to working principle, right?
Yes, sir.
Okay. See, when we are providing a supply to that of primary winding, then when the current it will be start flowing from primary winding, it will set up some flux. When this flux link with that of secondary side, then there is some EMF it can be induced in the secondary winding, right? If the EMF it can be induced in the secondary winding, so do you know that whether there is a total flux it can be linked with that of secondary? Total amount of flux which is created in the primary, whether this total amount of flux it will be set up in the secondary, or it will be linked to the secondary, or there is somewhat loss. Question लक्षात येतोय का माझा? Suppose in the primary there is some of the flux it will be created, that is phi amount of flux it will be created. This flux it will be linked to the secondary. Whether this all flux it will be linked to the secondary? ते सगळे फ्लक्स सेकंडरीला लिंक होतील का? Or somewhat loss is there? Always keep in mind. So I'm taking giving example. Always we are traveling, or it may be average we are missing that incident. What we can say, suppose always we are passing one message from one to another, so there is some loss of information, as you people know. Suppose the data, if the data it can be transmitted from one point to another point, एका पॉइंट पासून अनदर पॉइंट कडे काय करतोय आपण, डेटा ट्रान्समिट करतो. सो लिटल बिट डेटा इट कॅन बी वेस्ट, और इट मे बी देयर इज अ लॉस ऑफ इन्फॉर्मेशन. लॉस ऑफ इन्फॉर्मेशन होऊ शकते ना का? टोटल ते जे फर्स्टला प्रोड्यूस झालेले फ्लक्स टोटली सेकंडला हे होतील, लिंक होतील?
नो सर.
दॅट मीन्स काहीतरी त्याच्यामध्ये डिस्टन्स असेल, किंवा ती म्हणजे सपोज any higher authority giving any one of the instruction to anyone. Okay, म्हणजे काय केलं, एखाद्या हायर अथॉरिटीनं एका स्टुडंटला एक इन्स्ट्रक्शन दिली, and this student it can be passing this instruction to you people. Whether this student it is able to pass all the information to this all student? एखाद्यानं इन्स्ट्रक्शन दिली एका स्टुडंटला किंवा काहीतरी त्याला सांगितलं, एखादी आयडिया सांगितली, जशी या हायर अथॉरिटीनं या स्टुडंटला आयडिया सांगितली, तो स्टुडंट दुसऱ्या स्टुडंटला सेम आयडिया एक्सप्लेन करू शकतोय का जशी सांगितली तशी?
नो सर.
हा, दॅट मीन्स देअर इज सम लॉस ऑफ इन्फॉर्मेशन ना, का सगळंच त्याच्या ध्यानात राहील? सो दॅट्स वाय, so like that there is some loss of information when it is traveling from one to another, like that. So I am taking just one example. So see, that means the not total flux produced in the primary, it will be linked with that of secondary. There is that means there is some of the leakage in flux. Flux काय होईल त्याच्यामधला लीक होईल. Getting my point? लक्ष देते का बघा, प्रायमरी मध्ये प्रोड्यूस झालेला फ्लक्स जो आहे तो टोटल फ्लक्स सेकंडरीला लिंक न होता somewhat flux it will be leakage or somewhat flux it will be loss. That means suppose हा फ्लक्स जो आहे इथं क्रिएट झाला, हा एक पाथ घेऊन न जाता somewhat flux it will be linked with the other, somewhat flux it will be linked with the other, somewhat flux it will be linked with the other core, like that. Okay, so see, this flux it is totally not linked with that of secondary, somewhat leakage flux will be there. And this flux हा जो काही लीक झालेला फ्लक्स आहे किंवा जो लॉस ऑफ इन्फॉर्मेशन आपण म्हणतो किंवा लॉस झालेला फ्लक्स आहे, इट विल बी लिंक विथ द अदर कंडक्टिंग पार्ट ऑफ द कोर. आता कोर जे आहे हा ट्रान्सफॉर्मर आहे, या ट्रान्सफॉर्मर मध्ये वाइंडिंग आणि हे पण आयर्नचं बनलेलं आहे. So somewhat if there is a isolation failure or insulation failure, there is some of the conducting part of the core. Core चे काहीतरी conducting part असतील, right? So this flux it will be links to that of conducting part of the transformer or conducting part of the body of the transformer. See, some part of the flux, some part of this flux also get linked with the other conducting part of the core, that is like steel core or the iron body of the transformer. त्यातले काही फ्लक्स जे आहेत ते टोटली वाइंडिंगला न लिंक होता ते कंडक्टिंग पार्टला किंवा ट्रान्सफॉर्मरच्या बॉडीच्या कंडक्टिंग पार्टला काय करतील, लिंक करतील. And do you know that this flux it will be linked to any one of the conducting part? कुठल्याही कंडक्टिंग पार्टला जर ते फ्लक्स लिंक झाले, then it will produces some flux, or result of this, when it is linked with the other part, then on that part it will induces some EMF. त्या पार्ट मध्ये काय होईल, काहीतरी EMF इंड्यूस होईल. कन्सेप्ट लक्षात आला का बघा? See, when the primary it can be supplied by some voltage, at that situation some current it will be flowing from primary. When current flowing from primary, there is some flux it will be produces. This flux it will be linked with the secondary and it will produces a EMF in the secondary winding, but not a total flux produced in the primary, it will link with the secondary. That means there is a sum of flux it will be leakage or loss, and this flux it will be linked with the other conducting part of the transformer or body of the transformer. Okay, then what will happen? Similarly, पहिल्या कॉइल कडून दुसऱ्या कॉइलला किंवा सेकंडरी वाइंडिंगला लिंक झालेले फ्लक्स काय करतात, त्याच्यामध्ये ईएमएफ इंड्यूस करतात. सिमिलरली त्याच्यामधले जे काही लॉस झालेले फ्लक्स असतील, दिस विल आल्सो इंड्यूसेस और दिस विल आल्सो लिंक विथ सम कंडक्टिंग पार्ट, कंडक्टिंग पार्टला लिंक होतील and then it will also produces some EMF. त्या पार्ट मध्ये काय करतील, ते EMF इंड्यूस करतील. ओके, ड्यू टू दॅट इंड्यूस्ड EMF it will cause a small amount of current it will be flowing from that. Okay, see, बघा आपण ट्रान्सफॉर्मर ऑन नो लोड कंडिशनला कन्सिडर केला, ईएमएफ सेकंडरीला इंड्यूस झाला आणि सर्किट जर क्लोजला असेल तर त्याच्यामधून करंट फ्लो होतो, बरोबर? तसंच याच्यामधलेच काही फ्लक्स ट्रान्सफॉर्मरच्या बॉडीच्या कंडक्टिंग पार्टला लिंक होत आहेत, त्याच्यामुळे ते त्याच्यामध्ये ईएमएफ इंड्यूस करतायत, बरोबर? And when the EMF it will be induces in the some conducting part, it will produces some current or small amount of current it will be circulated in the transformer. So that current it is called as circulating current. Small amount of current generate will. So this current, it is called as a circulating current, or this current, it is called as ED current. So I want to tell a ED current, and due to that ED current, there is a some of the heat, some of the power, it should be dissipated in that conducting part in the form of heat, so that it is called as ED current loss. It is called as ED current loss. Okay, getting what is meant by ED current loss? Hello, ED current, all of you get what is meant by ED current?
Yes, sir.
So due to that ED current, आता ED current मुळे जे loss होतात, so that loss, it is called as ED current loss. And how ED current it will be formed? So instead of linking all the flux to the top secondary, some part of the flux, it will be links to the top some conducting part of the transformer, or some body of the transformer. Then when it will be linked with the top body of the transformer, it will induces some of the EMF in that body, and due to that induced EMF, it will produces a small amount of current, and this current, it is called as ED current, or this current, it is called as circulating current. And due to that circulating current, there is a some of the power loss in the form of heat. त्या circulating current मुळे त्याच्यामध्ये power loss will in the form of heat, so that we can call it as a ED current loss in the transformer. ED current loss in the transformer. Getting? So these are the two types of losses, that is hysteresis loss and ED current loss. So this similar, it will be happen in case of DC machine also. Getting, all of you? Give me reply. Getting now? Hello?
Yes, sir.
Okay. Now see, next one type of loss, that is we can call it as a variable loss, or it is nothing but a copper loss. Variable loss, or it is the copper loss. Okay. See, do you know that the copper loss, it is occur due to the ohmic resistance, or if the resistive material is there, like as a, we can call it as a, the coil, it is having and some of the resistance, or it may be a winding, it is having and some of the resistance. So some loss, it will be occur due to that ohmic resistance. This loss, it is called as copper loss. This loss, it is called as the copper loss. So copper loss for the primary winding, and do you know that the copper loss, it should be depends upon the value of current. Copper loss, it should be depends upon the value of current flowing from the winding मधून flow होणाऱ्या current वरती depend राहतील copper loss. So see, once the copper loss, it should be depends upon the current. So suppose it is different at the primary side, it is different at the secondary side. The secondary side ला different असतील, primary side ला पण काय असतील, different असतील. That means it is depends upon value of current flowing through that individual winding. त्या winding मधून flow होणाऱ्या current वरती काय राहतील, depend राहतील. Suppose we are writing the primary copper loss. So primary copper loss, it is nothing but the current flowing from primary winding. Suppose we considering the current flowing from primary winding is nothing but I1. Current flowing from primary winding, it is nothing but I1, and resistance of primary winding is nothing but R1. So that copper loss in the primary winding is nothing but I1 square R1. Similarly, if the secondary winding, current flowing from secondary winding is nothing but I2, and resistance of the secondary winding is nothing but R2. So the copper loss in the secondary side, it is nothing but I2 square into R2, like that. Okay. And here R1 and R2, it is nothing but resistance of each and every winding. That is resistance of primary winding and secondary winding respectively. And I1 and I2, it is nothing but I1 and I2, it is nothing but current flowing from primary winding and secondary winding. So see, from that two equation, we know that the copper loss, it should be proportional to the square of current. Okay. So see, that is PCU. If I am representing here PCU, copper loss, that means it is directly proportional to the square of current. If the current increases, or if the current increases, again the loss, that is copper loss, it will be increases. Okay, and the value of current, value of this current, it should be depends upon load. Okay, that means when load increases, the current taken from the transformer, it will be increases, and if the current taken from the transformer, it will be increases, then current taken from the transformer, it will be increases, again the copper loss, it will be increases. That means it is depends upon value of current, value of current, so that it will be vary with the current, it will be vary, म्हणजे current जर वाढला तर copper loss काय होतील, वाढतील. If the current decreases, copper loss, it will be decreases. That means it will be depends upon value of current, and it will be vary with the value of current, so that we can call it as a variable loss. So आपण त्याला काय म्हणतो, it is called as a variable loss. Okay, it is called as variable loss. So these are the some types of losses in case of transformer, that is iron loss, eddy current loss, and iron loss, eddy current loss, and the copper loss. Okay, now what is meant by efficiency? Okay, see, do you know that the efficiency of the electrical machine, efficiency of the electrical machine, it can be defined as output power divided by input power. So it is the ratio of output power divided by input power. You people already know the definition. Efficiency of the any electrical machine, it can be defined as it is the ratio of output power divided by input power. Okay, now the transformer are most highly efficient electrical device. Transformer जे आहे ते highly efficient electrical device है, because there are no any rotational motion, so it is static device. There are no any rotational part, so the loss occur in due to that rotation, like mechanical losses in that friction and windage loss, or it may be stray loss, it will be absent. Only iron and core loss and copper losses, it should be present, so that the transformer, as compared to the other electrical equipment, the transformer, it is having a more efficient device, that is more efficient electrical device. See, most of the transformer have full load efficiency, it is between 95 to 98%. So all of you note down this, because sometimes MCQ it may be asked. So most of the transformer, if even though it is running on full load, जरी ते full load ला run होत असतील, then also the efficiency obtained by such types of transformer, it is near about 95 to 98%, like 98.5%. Okay, now see, as the transformer being highly efficient, as the transformer is being highly efficient, output and input are very nearly same value. Okay, see, loss is nothing but output and input madla difference. Okay, the meaning of that is nothing but there is a minimum losses, or it is nearly equal to same input power, that is P in, it is nearly equal to P out. So that means there is a nearly or minimum losses in the transformer, and if the minimum losses in the transformer, efficiency of the transformer, it is more. Okay, see, a transformer is being highly efficient, output and input are having nearly same value, and hence it is it is practical to measure the efficiency of the transformer by using output divided by input equation. Okay, so output value of the transformer and input value of the transformer, it is nearly equal, so that it is impossible, it is impracticable, or it is impossible to measure the losses of the transformer by taking these two value, that is output value and input value, or by taking the ratio of output and input. So that we are using another one better method to represent the loss or to represent the efficiency. See, do you know that the formula, that is efficiency, it is equals to output power divided by input power, and you people are having an sum of the losses. We can rewrite this equation in this form. What is the output? Output is nothing but in the form of loss.
Input minus loss.
Okay, input minus losses. So input minus losses is nothing but output. So input minus losses divided by input minus losses divided by input. Now see, this denominator gets separately divided, so that input divided by input divided by input minus losses divided by input. Okay, this input get cancelled. That means 1 minus losses divided by input. So according to this equation, we are measure the efficiency of the transformer, because transformer having an high efficient device. So instead of using output divided by input equation, we are using 1 minus losses divided by input equation. 1 minus losses divided by input equation, so that we get the accurate value of efficiency. Okay, getting hello, लक्षात आलं का हे equation?
Yes, sir.
So from that equation we want to derive the condition of for maximum efficiency. आता या इक्वेशन वरून आपल्याला कंडिशन फॉर मॅक्झिमम एफिशियन्सी ची काय करायचे, डिराइव करायचे. ओके, वी वांट टू डिराइव द कंडिशन फॉर मॅक्झिमम एफिशियन्सी. See, suppose consider referred to primary side, that means any one of the referred side, and we want to derive the condition for maximum efficiency. Suppose consider a copper loss. Copper loss consider kara. So copper loss, it becomes I1 square into R1, and consider the constant loss or iron loss, it is represented by Wi. Okay, so see, according to efficiency formula, that is efficiency is equals to 1 minus losses divided by input. 1 minus losses divided by input. So it is equals to 1 minus loss. Put the value of loss. Loss is nothing but कोणते losses आहेत त्याच्यामध्ये, iron loss आणि copper loss. So sum of these two losses is nothing but total losses of the transformer, right? बरोबर ना? Total loss is nothing but sum of these two losses, right? So या दोन्हीची sum घेतली, that is I1 square into R1 plus Wi divided by input power. So input voltage into input current and power factor, it is nothing but input power, VI cos phi. Okay, now just separate out this. His equation I separate out केलं, that is 1 minus I1 square into R1 divided by, sorry, I1 square into R1. I will write here 1 minus I1 square into R1 divided by V1 I1 cos of phi 1. इथं प्लस आहे, हे मायनस आहे, मायनस इंटू प्लस, that means minus Wi divided by V1 I1 cos of phi 1. So याच्यामधला this I1 and याच्यामधला एक I1 get cancel. So remaining term is nothing but 1 minus I1 R1 divided by V1 cos phi 1 minus Wi divided by V1 I1 cos phi. Okay, now see, we get or we want to get the maximum efficiency. Maximum efficiency मला calculate करण्यासाठी, so I want to take differentiation of this equation. या equation चं मला differentiation घ्यायचं आहे with respect to current I1. So see, d efficiency by di1, it is equals to differentiation of 1 with respect to I1. Constant चं differentiation किती असतं with respect to I1? 0. Now I1 चं differentiation, that is I1 R1 divided by V1 cos of phi 1. I1 चं differentiation with respect to I1? Differentiation of x, d by dx into x. Differentiation of x with respect to x?
1.
1, no? So like that, differentiation of I1 with respect to I1 1 into all other term are constant, that is R1 divided by V1 cos of phi 1. Similarly, minus Wi divided by V1 I1 cos of phi 1. So Wi divided by V1 cos of phi 1 get constant, and differentiation of 1 upon I1 with respect to I1. 1 upon I1 चं differentiation with respect to I1 किती? dy dx 1 upon x differentiation with respect to x.
Minus 1 upon x square.
Minus 1 upon x square, like that. Here it is minus 1 upon I1 square. Okay, minus and here minus, it becomes plus. It plus il baga wi divided by v1 I1 square cos of phi 1, right? v1 I1 square cos of phi. To get the maximum efficiency, we want to equate this equation equal to 0. तो 0 से equate करावं लागणार आहे. So hence it is equated to 0. So put d efficiency divided by di1 is equals to 0. इथं 0 put केला. This minus term, it can be shifted to this side. That means r1 divided by v1 cos of phi 1, it is equals to wi divided by v1 I1 square cos of phi 1. Okay, this v1 cos of phi 1, this v1 cos of phi 1 get cancelled. Kai rahil? That is r1, only r1, it is equals to wi divided by I1 square. Okay, this I1 square, it can be shifted to this side. So equation becomes I1 square into R1, it is equals to wi. What is I1 square? What is I1 square R1?
Copper loss.
Copper loss. And what is wi?
Iron loss.
Iron loss. That means the condition for to get the maximum efficiency is the copper loss, it is equals to iron loss. We have already derived same condition in case of DC machine like generator and motor also. Generator and motor मध्ये पण same condition आपण derive केले. That means the condition to get the maximum efficiency in case of transformer, it is equal to the copper loss, it is equals to iron loss, or we can call it as a variable loss, it is equals to constant loss. Okay, variable loss, it is equals to constant loss. Getting? लक्षात आलं? Hello, give me reply fast. I am having lecture another. All of you getting, or is there any doubt? Hello, any doubt?
No, sir.
Okay, in this way we will conclude and we will stop here. Thank you.